All right, students, so I wanted to provide you with some additional thoughts on the thermochemical equation. And one of the main things I wanted to make sure I clarified for you was that this thermochemical equation, an example, the generic one that I used last time in the previous video, was this one here. Keep in mind that this particular equation, whether, once all the specific reactants and products are identified, this specific reaction is going to identify both of those reactants and products, all of them that are involved, and it's going to be balanced. And it will also identify a very specific delta H value for that particular reaction. And so the idea then is that when we look at the delta H value of formation for the products versus the delta H value formation for reactants, the difference then between them is what we're going to be calling here the delta H for the reaction, known as the heat of a reaction. Okay, and so overall though, for us, when we look at this here, the delta H of the reaction is going to be, well, first off, just make sure we identify this. This is going to be the heat of the reaction. Okay, and remember, from the heat of the reaction, we know from on this side that if we have a positive value, then it'll give us a certain indication that it's going to be endothermic. If it's a negative value, then we know that it's going to be an exothermic, because heat's going to be released in that particular instance where it's negative, and it's going to be required to be inputted into the system, in which case the value there will be positive. Now, the thing about delta H, though, is a couple of important points I want to make out here is that delta H is going to be dependent on the phase, okay, of the particular substance that you've got, okay? And so what does that mean? It means that depending on the phase, you could release more or less energy. So, for example, if you have a gas, yes, this will release a certain amount of heat, but when you compare this, say, to a liquid, the liquid then is going to be releasing more heat, largely because the liquid is going to have a lower kinetic energy, whereas the gas is going to have a higher kinetic energy. And so that extra kinetic energy that you're going to have in the gas, that's going to be lost as the material goes from gas phase over to liquid phase. And that reduction here, or rather I should say here, the high kinetic energy here is going to be reduced. The overall energy is no longer required there, because in going from a gas to a liquid, the kinetic energy is going to be released. All that extra that is no longer needed in the liquid phase that was required in the gas phase to keep it in that gas phase is then going to be lost and given up into the surroundings, and that's going to cause a loss of heat. So we'll typically see that there's going to be heat given off here. Okay, that's one thing that I wanted to point out for you. The other item that I wanted to point out to you is, again, just to remind you that whenever we form bonds, energy is always going to be released there. And if we're breaking bonds, that is always going to require energy input. So I'll just put that here one more time here. So bond formation is associated here with, put it this way here, a release of energy, and then the other item here is bond breaking. That's going to result in required energy. So you do need to put some energy into that. Okay. The other item that I want to put here, let me make some space here, make some items here a little bit smaller, is the last item that I want to make sure I identify for you is this notion about what about certain bonds. Like a lot of the compounds that we've talked about so far have been of several types. They were either ionic compounds or they were covalent compounds. And I want to focus a little bit more on the covalent compounds, because these is going to be the ones where there's sharing of electrons. And covalent compounds, these here are going to result in bonds that are going to be forming as a result of a more stable arrangement between the atoms, and that's going to require low energy. And so the covalent compounds require less energy, and therefore, and I'll put this in red here, therefore what's going to happen here is that you're going to release the excess. and I'm just going to abbreviate that as E. Okay, this excess energy that is going to be released here, this one has a very specific name. This name here is known to us as the Gibbs free energy. And we abbreviate this with a big capital G. And so typically, because there is a change in that energy, we usually say it's a delta G value. And so we'll explore this more in the next chapter when we talk about free energy, entropy, and whatnot. But in this particular context now, you can start to see that this idea of enthalpy, delta H, has a lot to do with the delta G value. Now, we did sprinkle a little bit of the discussion here when we're talking about the potential energy or the internal energy being a little bit about how the molecules are moving around in that particular system. That's the other piece of the equation, which is known as entropy. And so we need to put those three together, and you'll see that come up here in the video that we'll do a little bit later, that will kind of put those items together as one large equation so that we can see fully how temperature, how entropy or the movement of those particles are tied not only to the kinetic energy of those particles in solution, but also whether that's going to allow this reaction to progress spontaneously or not, and if there's any heat released as a result of that reaction that's occurring. All of these are important concepts for us to know, and so we'll continue to build this for you as we move forward. And if you haven't already subscribed, I urge you, please go ahead and subscribe. Keep watching, keep learning, and we'll see you in the next video.